So welcome back to the last series of slides now. It's the outlook of information systems for engineers. I'm going to do two things: wrap up what we've been seeing throughout the semester, on the very high level, very quickly, an overview, and then give you the transition and motivation to big data for engineers. And of course, I'd love for you to join Big Data for Engineers next spring if you're interested. Who already took Big Data for Engineers? None of you, okay, because you can take it in any order. Sometimes people take it first and then they attend it. Then it's basically the prequel of Big Data for Engineers. And Big Data for Engineers is the sequel, pun intended, of information systems for engineers. Okay, so this is what we have been doing through the entire semester. We've been looking at a database system. What is a database system? It is a system that stores and manages your data. But when we say database system, we actually include the data plus the management of the data. The data itself is called a database. So a clay tablet was actually a database. The database management system, that's the software that manipulates the whatever is on disk in order to provide you with the database abstraction layer, right? So the database management system is PostgreSQL in that case. And the database is everything that there is on disk and that you see as tables, all right? And the whole point of having a system like that is to make life easier for you, because all you need to do is think in terms of tables, and you just manipulate tables, have a high-level language SQL to manipulate tables, and you do not have to go through all the trouble of trying to directly manipulate your data on the disk and having to re-implement everything yourself, right? You can just rely on what other people have done. So this is the principle of data independence, that you have a logical data model, the relational table, and then hidden from you, it's actually stored on disk, and now you know it's stored in chunks of 1 gigabyte with pages in the chunks and so on. Okay. Since we abstract things away, we like to think a bit mathematically, and so we looked at a mathematical definition of a table or relational table. So what is a relational table? Well, a relational table, in short, I basically told you it's a set of maps, right? Every map is one row. It's called a map. It's mapping the name of a column to the value in that column, and that's it. So it's a set of maps. And we have a constraint, 3 constraints actually, typically in relational systems. The first constraint is that all of the maps in the same table must have exactly the same columns, the same supports. That's how you store it efficiently on disk. The values in the maps must be atomic. You cannot nest maps in maps in maps in maps. That's not okay. You cannot also nest tables in tables in tables. That's atomicity. And the third constraint is that within one column, it's all the same type. In a column, it's all integers. In another column, it's all dates. In another column, it's all strings, and so on and so on. Under these 3 constraints, the set of map is a relational table. So this is the definition that I gave you, knowing that in textbooks, there's an alternate definition that defines a relational table as a mathematical relation over the domains of the columns, right? I find it a bit less intuitive, but this definition right here has the advantage that it's very intuitive to then go to big data. Because when we go to big data, we just relax the 3 constraints and that's it, and you get big data. So we saw that there is a restaurant menu of the types that you can have in the columns, and then you can pick from. It's a bit of a jungle for several reasons. First, because you very often have synonyms of several ways to name the same type, so it's a bit of a mess sometimes. Different systems can also have different names for the type, but you just have to live with that, and that's why you have documentation. But you should still know what's on here is just an excerpt of that. These you should really know, at least. Maybe have them in mind. Okay. Then we saw that with the system, we can actually practically create tables, modify tables, drop tables. Creating a table means that you provide a schema. So you say, okay, these are my column names. And for every column, this is the type of the column picked from that menu. You can modify a table by saying, okay, add a column, remove a column, and so on and so on. Or you can drop a table and just throw it completely away. So this is called DDL, and DDL means data definition language, exactly. Then you have data manipulation language. So this is when you actually manipulate tables. And you can, for example, insert a tuple in a table, delete a tuple, update a tuple, or query tuples. Then this is SQL, and you have the whole algebra, right? We saw that it's good practice to spread your data over multiple tables. And when you do that, you have a link between the tables because the table can point to another table. This is called the primary key foreign key ID, right? So you can have persons that have the primary key AHFAO, that is their identifier. And you can point to that from another table that's called the foreign key. For example, you have the taxes and you map the social security numbers to fiscal residence. Then you have a foreign key pointing to a primary key. Then we have a whole mathematical framework called the relational algebra. It's exactly like algebra or what you have in mathematics that you manipulate numbers, but that's the beauty of mathematics is that just like you manipulate numbers, you can manipulate tables. So this is the universe of everything you can do with tables. So we saw that since these are sets of maps, then you can do union, intersection, subtraction. There's an S too much. You can have filtering queries like selection, selecting rows, or projection, then you're filtering columns. You can rename attributes and relations, and you also have these binary queries in the sense that they have data coming from multiple sources, multiple tables, so you can do the Cartesian product. Be careful though with the Cartesian product. If you have a billion tuples here and a billion tuples there, and you do the Cartesian product, you're going to crash your machine, right? So always keep that in mind. A natural join is going to match. It's like the Cartesian product, but only with the tuples that match. And especially if you have this foreign key, primary key, this is when you want to do a join on the primary key, foreign key. And you have the theta join if it's more generic than the natural join. So the natural join is when you have the same column names on both sides. And the theta join is hence a customized criterion for joining. Okay. So this is the pattern, just again, as an illustration of joining. And again, typically you do that when you have a primary key and a foreign key that you want to join together. So you get a bigger table there. And of course, this bigger table, it's called denormalized because it's not going to be in a normal form in the same way that the original tables are. Right. We saw you can also group. In fact, grouping is super powerful. Statisticians love to group because then you can aggregate things by Gemeinde, by canton, and so on if you want to run some statistics. You can sort data, but you have to be careful because then you need to tweak the semantic a little bit because if you have sets of maps, there is no order, so you cannot sort anything. So you need to say, okay, now it's not going to be sets of maps, it's lists of maps. We just change the semantics of the table by saying, okay, the order actually matters of the rows, and then you can actually sort with order by in SQL. All right? So then we saw that there's two kinds of languages, imperative languages and functional and declarative languages, on the other hand. Imperative languages include Java, Python, and so on and so on. You basically tell the computer what to do step by step. In a declarative language, you just ask for what you want directly. Many people make the mistake of directly using, especially now it's the hype with Python, of saying, okay, I'm going to query my data with Python. Python is an imperative language. It's much more difficult to actually optimize than with SQL automatically. So by using a declarative language, when you query data, you are basically doing yourself a favor because then it's going to be magically fast, especially with indices, as we saw. It's going to be magically fast because that's the database management system that's going to make it fast for you, right? So that's the benefit of a declarative language. So we saw that SQL looks like this. In fact, now you know all the clauses. It's select, from, where, group by, having, order by, limit, offset. Learn that by heart, exactly in that order. Select, from, where, group by, having, order by, limit, offset. Some are optional. You don't need all of them at the same time, but this is the order in which it is. So SQL, in that sense, is a bit constrained or restricted to that very order. So here you have an example with just group by and having, right, in addition to select from. So this is an aggregation. Then in the from clause, you see that this is where you do the joins. So you have plenty of keywords that we studied in details on all the ways you can do your joins: left outer join, right outer join, full outer join, and so on and so on and so on. And in on, you can specify your criterion, right? So this we've seen in details. And then we took a break from practical stuff, came back to theory. Why? Because this also has to do with good practices. once people understand that instead of directly using Python or language, you should use a database management system, you might still make the mistake of not designing your schemas correctly. And when I say correctly, I mean in terms of best practice. If you don't pay attention and you create huge schemas with too much information that in the same table you put your products, your customers, and everything, the problem is that's going to duplicate a lot of data. And when you insert an update, you have to remember to update at all the places that the data is duplicated. So you quickly run into issues. For this reason, knowing a bit of theory helps. And what the theory says on the high level is that you should spread your data over multiple tables, and every table should be doing one thing. You have one table for the products, one table for the customers, and one table for the inventory, one table for the order, and so on. These tables are all linked via this foreign key primary key mechanism, right? And we need a theory that supports you in doing that and tells you when you can tell this is a good practice. This is a good way of designing my schema. And the way this was done is with the concept of functional dependency and the concept of normal form. And we saw in particular the Boyce code normal form. So the concept of functional dependency is when you have a column that depends on another column. For example, the address of somebody might depend on their social security number. That's an example of functional dependency. The price of the product might depend on the part number of the product, for example. The part number is the fancy name that basically identifies a specific kind of product. We have a question, I think, on Zoom.
Yes, how important are the other normal forms compared to the Boyce code normal form?
I would say that, so the way that normal forms are built is they are in increasing order of constraints. You have the first normal form, the second normal form that constrains a bit more. Basically, the second normal form says that when you have attributes that are in nowhere part of the candidate key, so the attributes that are really kind of secondary, these attributes cannot depend on a subset of the candidate key. It must depend on the full candidate key. That's what the second normal form says. As you can see, it's a bit weaker than the Boyce code normal form, right? Because you can infer at once that if you have the case that attributes, if you know that you're in Boyce code normal form, then you can only have functional dependencies with a super key on the left, right? But if you have an attribute that depends on part of a candidate key, then it means you have a functional dependency that's not a super key on the left, because that's only a part of a candidate key. And by definition of a candidate key, it cannot be a super key, right? Because a candidate key is a minimal super key. So anything below that cannot be a super key. So you see that the normal forms are basically like by increasing level of constraints. So the first, the second has more constraints. The third one has more constraints. Boyce code even more. I think it's often called 3.5 normal form, like 3.5. Then there is another one that's the fourth, the fifth, the sixth. I didn't want to scare you with all the details of all these normal forms because I just decided to teach you the Boyce code normal form because this one is really easy to spot, right? It's very easy to see whenever you have a functional dependency, it's not a super key on the left. So I would say that for the purpose of what we are doing to give you the intuition of things, that's enough. But some people also like to study more in details and understand more the details of normal forms. I'm not sure if that answers the question on Zoom.
I think the question also goes into the relevance, like how important are the others? Like why would we not use, like would we ever use anything other than the Boyce code normal form?
I would call it a matter of compromise. Basically, ideally, you should aim for the highest possible normal form. The highest possible normal form makes your life easier and easier. But in real life, that's not going to happen, right? So ideally, if you are in a company and you manage to have everything in Boyce code normal form, that's going to make a lot of people happy, right? But in practice, in some cases, because of the real world or because the way that the data work, that would be too much work to put it in the Boyce code normal form. Then you just give up on some of the constraints and go to a lower normal form. So I would say that this is what this hierarchy is useful. It's basically a matter of go as high as you can, but it's okay if it's not all the way up, right?
And what would prevent you from going all the way up?
I would say the real world. This is really the real world, because if you think in a very high normal form, you have an idealized data set. But in the real world, that's not how things work, right? When you are in a company and you want to store data from the real world, you don't control everything about the data coming in. You might have a few imperfections in the data. You might have a lot of trouble there. So that's the intuition of it, right? It's really the real world, modeling the real world. Yeah.
I guess that answers the question.
Let me give you an answer. An example. In Switzerland, for example, if you want to identify a Gemeinde, the name is not enough. You also need the PL set, the zip code. Like, I don't know, I was about to say Küsnacht, but I think there's still an S less or more. What's another example of Gemeinde that is duplicated? Altstetten, there's also two. Okay, yeah. So you can disambiguate based on the zip code, or you can also disambiguate based on the content, right? You can say, oh, Pfeffikre is another one, Pfeffikre Schwyz. There's also a Pfeffikre in Zurich. Is it in Zurich? So that's how you disambiguate. And you see in the real world, you could use the Postleitzahl, you can use the name of the Gemeinde plus the content. So you see, this is the sort of things that is not as ideal as you would have in a purely mathematical universe. Yeah. Okay?
Yeah, thanks.
All right. So then when we had the functional dependencies, we started playing games by picking a set of attributes, and then we try to fill the bag with as many as we can by looking up the functional dependencies. That's called the transitive closure. Basically what that bag is, it's just that set, I should be more precise, that set is, it's all of the attributes that are dependent on the original ones. So when you have A and B, you're asking the question, okay, if I know A and B, what is everything I know? And in that case, you know A, B, C, D, E, I, J, K, L. And the way we know that we know is that we know these functional dependencies on the left. So then we saw that we can actually work directly on an axiomatic level. So it's a bit more abstract, but we can work with rules on these functional dependencies and change them. Then we looked at the Boyce code normal form. And again, that's one I picked because, again, as we said, there's plenty of different normal forms. The typical ones that people use is either the third one or the Boyce code normal form. I think these are the most popular one. In fact, the third normal form is so popular that you sometimes see 3NF, meaning third normal form, that people just abbreviate it in that way. But again, I picked the Boyce code normal form because it's very simple to explain, the Boyce code normal form. So it's a Boyce code normal form if all of your functional dependencies, they have superkeys on the left, the non-trivial ones, of course. Okay, and then we saw that's also why there are several normal forms, and that maybe also answers the question you asked earlier, is that ideally we want to be in high normal form. We also want to have a lossless join, in the sense we don't lose information when we split the data across tables. But we also want to preserve the dependencies. And this, in fact, is something that prevents you from going too high in the normal forms, right? This is another aspect. If you want to preserve some dependencies, that prevents you from splitting the table. You're stuck, for example, in the third normal form, you cannot go all the way to Boyce code. So these are also compromises that you make. And that actually would not be because of the real world. That's actually more of a mathematical aspect. Yeah, that would be a second answer to the question that you asked. That the more you constrain, the higher the normal form. There are some things that you have to give up. Okay, then we saw in practice when you have a database system, it's implemented on multiple levels, on multiple layers, and typically in an enterprise setup, you have 3 levels of servers that you have. You have the database servers, that would be PostgreSQL. You have the application servers that are typically running Java EE, PHP, and so on. And then you have the web servers that basically serve the HTML pages that are automatically built by the application servers. They serve the images, they serve the sound, videos, and so on and so on. And then you have the internet. Okay, next. What we saw is that we can accelerate queries thanks to indices. Indices are what you find at the end of a book when you want to quickly look up the words and see on which pages they are. And in fact, we do exactly the same thing with database systems. An index is an additional structure. It's something on top of things. It's redundant, right? It's an additional structure, but with this additional structure, you can actually look up things much, much, much quicker than you would do on the original table, because otherwise you need a full scan. You need to read the table entirely. With this additional structure, you can accelerate things, and we saw that with the tree-like indices, the B+ trees, we can do it in logarithmic time. That means that every time you multiply the size of your data by 10, you only add a constant amount of time to the lookup. You don't multiply the time, you add time. And we saw the other kind of index, that's the hash index. This is even better because here, no matter how large your data is, it's still going to be as fast to look it up. If you have million, billion, trillion, still takes the same amount of time to look it up. But hash indices do not support intervals. You cannot do queries like, or you cannot accelerate queries that say, for example, age between 20 and 30. That you cannot do with a hash index. You have to use a B+3. Okay, then the data models. There's plenty of shapes. There's relational model with tables, the data cube model. We've looked at these two, and we did not look, this is for big data engineers, at trees and graphs, right? So tables were most of the semester, but we spent last week looking at cubes. And looking at cubes, we realized that it's a completely different universe. You don't select and project there, you slice and dice. So slicing and dicing means slicer, you take a slice of the cube, and then when you have 2 dimensions left in your slice, you nicely project it on the rows and columns and display the data in a business user fashion, like this, in a fancy fashion. Almost every spreadsheet software has a feature like that called pivot table, and you just drag and drop your dimensions to create that view. We saw that OLAP can be implemented on top of a relational database or natively, but I've showed you the left one. So on top of the relational database, rollup, we saw that we can do it in SQL, right? So you can actually store your entire cube as a facts table, one little cell of the cube on every row that gives you a facts table, right? With multiple measures like profit, revenue, and so on, you just get multiple such columns. We've seen that we like to normalize things. So when we are in an OLAP setup, so then you have what's called the star schema or the Snowflake schema if you overdo the normalization. With the fact table in the middle, every dimension is a foreign key that points to the satellite tables through their primary key. You see again here, foreign key, primary key joining, it's all used directly in this design. Okay. Then we saw that we can also denormalize the fact table with hierarchy structures. We saw that we can use SQL in order to compute the subtotals in that way. That's what I told you just a few minutes ago, so I don't need to repeat. It's the multiple level of storage. So what do you need to study for the exam? You need to study the slides that we've been seeing, the recordings, they're all on YouTube, the textbook. I sent an email with all the correspondence to the chapters. I strongly recommend you take the time in the exam preparation period to read the book chapters. It's pretty much the same thing as I've been telling you, but if you read that told by somebody else, explained in a different way, it's going to help you connect things and maybe see things you might have been missing before nicely in your mind. So I strongly ask you to read the textbook, and you have the mapping with the chapters that is in the Moodle as well. Hector Garcia Molina, by the way, he was a Stanford professor. He had a honorary doctorate from ETH Zurich. I remember in 2007, he visited us. Theoretical exercises, practical exercises are also relevant. The clicker questions to some extent are also relevant, and we'll play a quiz even with these questions. All right, so the sequel of the course is Big Data for Engineers, taking place in the next spring. And we are going to look at something different, the semi-structured data world. It's when data is not a cube or a table, but it's more like a tree. The idea is that a lot of technologies were invented recently in the 2000s. That's what you might have heard of NoSQL. Who heard NoSQL? It was a buzzword back then. Maybe now the buzzwords are more like blockchain and AI and machine learning, right? But back then, NoSQL was a huge buzzword. Everybody was talking about it. So we are going to study this technology of the 2000s and 2010s. And mostly in big data, what happens is that we have huge volumes, much more than fits on a machine. We have huge variety of data, multiple shapes, and we have velocity. It means that data is flowing amazingly fast all over your cluster. So these are the three factors, the three V's of big data. So in terms of volume, I'll ask you to learn everything by heart of these prefixes. By the way, Rona Quetta are the new ones, very recent. So now we're all the way to 10 to the power of 30. So you must know these by heart in order to know the scales of your data. So especially for big data for engineers. Let me check if there's a break, I think, but checking the time. Still have 2 minutes. So let me tell you about that. In order to explain why big data, why do we need a different course for big data? Why is it not just the same as PostgreSQL? It has to do with the evolution of the capacity, the data we can store, the throughput, and the latency. So the capacity is how much data can we store. It's basically the size of your hard drive. The throughput is how fast can we transmit data. It's the speed of your internet connection, or it's the number of bytes you can read from the hard drive in 1 second. And the latency is when do you start receiving data, right? For example, on the disk, the latency is the time you need to wait for the rotation of the mechanical drive to land over the reading head. So there's a bit of latency. And if you look at the evolution of these things, if we go all the way back to 1956, that was the first commercially available hard drive. It was called the IBM Ramac 350. That was huge. It's like a meter 50 of diameter. So it's really like, if I would have it here, it would be enormous. That's one of these rotating plates in that drive. Compared today to this much smaller, I think that's I think there's now a 26 terabytes, but this is the other magnitude. Now we have this super small hard drive that fits terabytes of data. This one had like 5 megabytes of capacity. That was ridiculous, right? And from here to here, the evolution actually dictated big data, but that I will explain after the break and before the quiz. So let's take a break, 15 minutes. Then I'll finish that, and then we'll play the quiz, right? So see you at 11:15.